Hi, let's take a look at an interesting property of right triangles. Suppose we draw a right triangle and we label the sides A, B, and C. The side C, which is the side opposite the right angle, is called the hypotenuse. That's Hypotenuse. Now, in terms of the angle theta, which I will select this angle and call it theta, then the side B is the side opposite the angle theta, and the side A is the side next to or adjacent the angle theta. Now let's take a look at the ratios of the sides of the right triangle. Let's pick, for example, the ratio of the length of side B to the length of side A. We could write that as B divided by A. Now, here's the interesting property. If we extend this side and we extend this side, even if it goes through the words, and then we close out the right triangle, we see something interesting. We can call this side right here B prime, and then we call this new side here A prime. And here's the part that's really interesting. The ratio of B prime to A prime is the same as the ratio of B to A. So what that means is that the ratios of the sides of the triangle depend only on the specific angle theta that is selected, as long as you're working in a right triangle. So in trigonometry, the ratios of all the pairs of sides are given special names. There are 6 of them. Let's go through them and define them in terms of the sides of the triangle. The first one is called the sine, and it's spelled S-I-N-E. It's abbreviated S-I-N. And the way it works is this. The sine of theta is the value given to the ratio of the opposite side divided by the hypotenuse. And we'll just abbreviate here, opposite divided by hypotenuse. Okay? The next function we're going to look at is the cosine function. It is abbreviated COS. And so the cosine of theta is the ratio of the adjacent side to the hypotenuse. The next one is called the tangent. It is abbreviated TAN. And the tangent of theta is the ratio of the opposite side to the adjacent side. All right, that's half of them. There are 3 more. The next one is called the cosecant, C-O-S-E-C-A-N-T, abbreviated CSC, and the cosecant of theta is the ratio of the hypotenuse to the opposite side. Okay. The next one is called the secant. It is abbreviated SEC, and the secant of theta is the ratio of the adjacent side to the ratio of the hypotenuse to the adjacent side. And then the last one is the cotangent. Abbreviated COT, and it is the ratio of the adjacent side to the opposite side. these 6 ratios and their associated names in terms of angle theta are called the right triangle definitions of the trig functions of theta. You need to study these carefully. You need to practice writing them over and over again till you're absolutely comfortable with them. Now let's take a look at an example of how this is used. Use the definitions to find the trig functions for the given triangle. All right, so what do we have? We have a right triangle, we have a designated angle theta, and we know that the side opposite theta is 2 units long, and the side adjacent to theta is 5 units long. So what's missing? Well, of course, what's missing is the hypotenuse, this side right here. We know this is a right triangle, so let's find the hypotenuse. We want to know the length of side C. All right, now what's the relationship? Think about it. What's the Pythagorean theorem say about the relationship of the 3 sides? Right. It is C squared equals A squared plus B squared. We're looking for side C, so we're going to write C squared is, A is 5, so that's 5 squared, and B is 2, so that's 2 squared. So C squared is 25 plus 4, which is 29. Now, this is an algebraic expression, and so when you take the square root of both sides, algebraically, unrelated to geometry, you would get plus or minus the square root of 29. But because this is the length of a side of a triangle, there's a geometric restriction here, which says, of course, the side of a triangle can't be negative. And so in our case, C is the square root of 29. By the way, you will do this process many times in trigonometry. You may want to start trying to think of doing it mentally. And here's what you would do. You're looking for the hypotenuse. You square this side, 25, this side, 4, add them together, 29, square root of 29. And so get used to practicing this mentally. It'll save you a lot of time. All right, so back to the problem. We need to use the definitions. Do you remember them? If not, get them out in front of you and then practice so in the future you will remember the 6 trig functions. Okay, here we go. We start with sine. Okay, the sine of theta is, and say it to yourself, it is the opposite over the hypotenuse. So that's 2 over the square root of 29. Okay, now we're going to stop for a second. Unless you are specifically told to do so, there is no reason why you have to rationalize this denominator. It is perfectly acceptable to leave this unless you have instructions that tell you otherwise. Okay, the cosine of theta is adjacent over hypotenuse. So that's 5 over the square root of 29. And then the tangent of theta. Okay, say it to yourself. What is it? It is the opposite over the adjacent. So it's 2 over 5. All right, next 3. Cosecant of theta is the hypotenuse over the opposite. Square root of 29 over 2. Be careful when you write this here. The 29 is under the radical. The division sign in the 2 is not. Okay, next one is secant of theta. And the secant of theta is the hypotenuse over the adjacent, correct. So it's the square root of 29 all over 5. And the last one is cotangent. And the cotangent of theta is equal to the adjacent over the opposite. And so it is 5 over 2. Okay, this satisfies the directions, but let's look at what we have here. These are the 6 trig functions of theta for this triangle. We calculated these using the definitions, but You've probably noticed at this point that there's a certain relationship between the 6 of these. So the next thing we're going to do is we're going to take a look at a little bit faster way to get some of these by using the relationships between them. All right, I have here on the board the definitions, the right triangle definitions of the 6 trig functions. What we want to do is look at the relationships. We're trying to see how of these fit together and how one is related to the other. Okay, well, first of all, I noticed that sine divided by cosine, well, what would it be? It would be this expression divided by this one, and if you simplified it, hypotenuse and hypotenuse would cancel, and you'd end up with opposite over adjacent, which is tangent. Okay, so we notice that relationship. So we say that the sine of theta divided by the cosine of theta is equal to the tangent of theta. All right, now let's look at these. What is the relationship between sine, cosine, and cotangent? Okay, and obviously there are lots of relationships, but there's some that seem to be used more often than others, so those are the ones we're going to point out here. Okay, what happens if you divide cosine by sine? Well, again, hypotenuse cancels, but you get adjacent over opposite, which is cotangent. So we're going to write down this one. Cosine of theta divided by sine of theta equals cotangent of theta. All right, these two in particular are what are called the quotient identities. Okay, and as I said, there are others, but these are the most used. Okay, now let's take a look at the reciprocal identities. Okay, well, sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite. So what that means is that cosecant of theta is equal to 1 over the sine. And for that matter, the sine of theta is equal to 1 over the cosecant of theta. But once you learn the identity one way, of course, you can simplify it to get the other one. Okay, what else do we see? Well, we see that the secant of theta is equal to 1 over what? Cosine. And then what about the cotangent? The cotangent of theta is 1 over the tangent of theta. And these very descriptively are called reciprocal identities, because that describes the relationship. Okay, the next group of identities take a little bit more thought, but not that much. What happens if you take the sine and you square it and the cosine and you square it? Okay, well, it's not quite as obvious from these definitions, but if you're curious about where this comes from, you can go back to a previous example that we did and actually take those values we did with the triangle that had the 2 and the 5 and the square root of 29, and you can square the values and see what happens, and I'll show you the result. The result is that if you take the sine and you square it, so the sine of theta squared, and you add it to the cosine squared of theta, you will get 1. Notice that this is really the same expression as the sine of theta squared. It doesn't mean anything strange like square a number and multiply it by theta. This is all one term raised to the second power, but this is how it's written. Okay, the next relationship that follows this pattern is that if you square the tangent of theta and you add 1, you will get the value of the secant squared of theta. And the third one is that if you take the cotangent of theta and square it and add 1, you will get the cosecant squared of theta. And these are called the Pythagorean identities. together this group. This whole group together. These are called the fundamental identities. You need to practice these. You need to be very familiar with them. You need to be able to write them down. You need to be able to recall them with barely any effort whatsoever. Now, let's take a look at how this can be used. Example 2. Use identities to find the exact value of, and we have two expressions. Now down here at the bottom of the board, I have the fundamental identities that we developed in the last segment. I'm going to just leave them here so that we can refer to them. Okay, so let's see what we have. We have the tangent of 75 minus, and then we have the sine of 75 degrees divided by the cosine of 75 degrees. Okay, so what's the identity that we can use here to simplify this? Well, sine of theta divided by cosine of theta is tangent of theta. And since these angles are the same, both 75 degrees, we can rewrite this expression by copying over the first term, making no changes, and then replacing the second expression with the tangent of 75. And at this point, it's pretty obvious that the exact value is 0. All right, let's look at the second one. As soon as you see the sine squared, pi over 5, and then secant squared of pi over 5, where are you going to go? Sure, you're going to go to this expression here. Okay, now we have sine squared and secant squared. So that is a possibility of the first one or the second one. Well, let's see which one has the most promise. Well, we know that secant is related to what? Look around. Secant is related to cosine. They're reciprocals. And if I can change a secant expression to being defined in terms of cosine, then I should be able to use this identity second. All right, so first thing I'm going to do is I'm going to copy the first term. And then I'm going to rewrite the secant squared pi over 5. Let's see, secant and cosine are reciprocals. So if I have 1 over the secant squared of an angle, I should be able to write it as the cosine squared of the same angle. Now this is actually the reverse of the identity that I have written here. I'm actually using the cosine of theta is 1 over the secant of theta. But that's fine. Once you know this one, you can get the other one. And then what do I have? I have sine squared of an angle plus cosine squared of an angle is 1. All right, let's look at another example of how we use these identities. Example 3. Given that the sine of theta is 1/4 and that theta is an acute angle, find the exact value of the remaining 5 trig functions. All right, so let's take a look at what we have. So we have a right triangle. We know that because we're using trig functions, and of course they are trig functions of right triangles. So we have a right triangle. Let me just draw a little bitty one right here, just enough to label the sides. Here's angle theta, and the sine is 1 divided by 4. Think about the definition again. So that means 1. So that means this side is 1, and the hypotenuse is 4. So what's missing is this side. Now remember how I told you to learn how to do this mentally? Let's see if we can find this side mentally. It would be c squared equals a squared plus b squared. So what that means is this side squared is that one squared minus that one squared. So what do we get? We get 16 minus 1, which is 15, which means this side is the square root of 15 units. 16 minus 1, and then square root of both sides. Okay, so what we have is opposite, adjacent, and hypotenuse. But we have all of this. So we start. The sine of theta is given. Notice how every time I do this, I write 3 down, 3 more down in the same order. It helps for you to remember these things if you are very orderly and organized about how you do this. Okay, now, the cosine of theta. It is going to be adjacent over hypotenuse. Now, use the identities. What is tangent. Tangent is cosine divided by sine. And the 4's will cancel, and what you get is 1 over the square root of 15. Oops, let's look at that. Tangent, I think I said cosine over sine. Ooh, no. Tangent is sine over cosine. All right, so the tangent of theta, let's look at it again. It's sine divided by cosine. You do have to be careful when you do this because, of course, it's the same words over and over again. So it would be 1/4 divided by 15/4. The 4's cancel, and so what you do is write 1 over the square root of 15. Okay, now basically at this point you've got all of them because the next 3 are reciprocals of each of these 3. So as long as you are careful with what you write, the cosecant of theta would be the reciprocal of 1/4, which is 4. The secant of theta is the reciprocal of the cosine. And the cotangent of theta is the reciprocal of the tangent. All right, now before you stop, you go back and you check all of this. This was given. Cosine is this over this. Tangent is that divided by that from this identity. Cosecant is the reciprocal of this one. Secant, reciprocal of this one. Cotangent, reciprocal of this one, and you've got all 6. Let's look at another property of right triangles. Let's discuss the relationship of cofunctions of complementary angles. All right, from geometry, you may remember that complementary angles are angles that have a sum of, do you remember? Yes, 90 degrees or pi over 2. Okay, so let's remember that the word complementary means that 2 angles have the sum of 90 degrees or pi over 2. All right, so in this right triangle, we have the sides labeled A, B, C is the hypotenuse. This is the angle theta, right angle. So the question is, what is this angle in terms of theta? Well, I gave it away a little bit when I talked about complementary angles because if you remember, the sum of all 3 angles of a triangle is 180 degrees. So if it's a right triangle, then that means the sum of these 2 angles is, yes, 90 degrees, which means these are complementary angles. So what that means is that I can label this angle right here, and I'm going to bring it out to here. I'm going to label that angle as what's left. The sum is 90, so I could say theta plus this angle is 90. So what's left for this one is 90 degrees minus what was used here. Or I could write it as pi over 2 minus theta. Okay, now you have to get used to this notation so that when you see it, you can spot it. So if this angle is theta, then the other acute angle in the right triangle could be written as 90 degrees minus theta, or it could be written as pi over 2 minus theta. All right, now let's look at cofunctions of these complementary angles. All right, let's start with theta. Okay, with theta, let's just take the first one. So we'll say the sine of theta is. Okay, now remember the definition. The sine of theta is the opposite over the hypotenuse. So that's the length of side B divided by the length of side C. All right, now what is the cofunction for sine? Think about the word co. Okay, sine, the cofunction is the cosine. What is the value of the cosine? But we're not going to take the cosine of theta. We're going to look at the cofunction of the complementary angle, which is this one. Now I can write it in either way. I'm going to choose to write it as pi over 2 minus theta, but I could have put 90 degrees minus theta. And so what is the cosine of this angle? All right, now think. Cosine is adjacent over hypotenuse. I'm using this angle, so this is the adjacent side. See, this is the opposite side, this is the adjacent side. So the cosine of this angle is B over C. Okay, well, as soon as I get to this point, what do you realize? You realize that co-functions of complementary angles are equal. Okay, so what we have is this. We have that the sine of theta is equal to the co-function of the complementary angle. Now, if we had all day, we could go through all of the other trig functions, but I think by this process you can see that I could write a similar situation for, let's say, the tangent of theta. And I could write this as equal to the cotangent of the complementary angle. And I could continue along with secant and cosecant. So I could write that the secant of theta is the cosecant of the complementary angle. All right, these and the rest of the relationships show you that co-functions of complementary angles are equal. Let's take a look at an example of how the complementary angle theorem can be used to simplify an expression. Okay, now you need to remember the fundamental identities, and I have some of the cofunction of complementary angles expressions still listed down here, so we can refer to this. Okay, A says the cosine of 40 degrees divided by the sine of 50 degrees. Okay, well, it should jump out at you that the sum of 40 and 50 is 90, and so these are complementary angles. All right, so what that means is we can rewrite this expression. Let's go with the numerator. So the cosine of 40 degrees is equal to the cofunction of the complementary angle. And that's because if this angle is theta, then this angle is 90 degrees minus theta. And then we copy over the denominator, and immediately we see that what we have here is equal to 1. All right, let's look at B. 1 plus the tangent squared of 5 degrees minus the cosecant squared of 85 degrees. Okay, what hits you first? Well, maybe it's the fact that 5 degrees and 85 degrees are complementary angles. So we know somewhere we're going to use one of these. But we have tangent and cosecant, and none of this is going to be direct. So what we're going to have to do is find an identity, rewrite some of this, then use one of these parts of this, one of these complementary angle expressions. Okay, there are a couple of ways you can go here. I would think that the most efficient approach would be to recognize right away that this expression can be rewritten as what? Now think about the Pythagorean identity. Tangent squared of an angle plus 1 is equal to what? Okay, go through them. You should remember that it is secant squared of this angle, which is 5 degrees. Okay, then now I have minus cosecant squared of 85 degrees. Well, what can I do now? How can I write, say, this one in terms of 5 degrees? Well, this is cosecant. I could change either one of them. Actually, I just chose to do this one. I could rewrite this as the secant squared of 5 degrees, and then I know I've got it here because I've got the same two expressions. Subtract, and I get 0. All right, let's take a look at another example. This time, our angles are given in radian measure. C, we want to find the exact value of the sine of 5 pi over 12 divided by the cosine of pi over 12. Well, 5 pi over 12 and pi over 12 are not special angles, so we're not going to be able to find the exact value exactly as the expression is written. So let's look at the two angles. So I'm going to walk over here and I'm going to examine 5 pi over 12 and pi over 12. What if I added the two angles? Well, I would get 6 pi over 12, which is pi over 2. So now, what do we know about these two angles? They are complementary angles because the sum is pi over 2. Well, what do we know about complementary angles? We know that cofunctions of complementary angles are equal. So let's look. Here are some of the cofunction identities. We can rewrite the sine of 5 pi over 12 as the cosine of pi over 2 minus 5 pi over 12. Okay, and then I'll just copy the denominator over. Okay, and because of what we did over here, we see that pi over 2 minus 5 pi over 12 is the cosine of pi over 12. The denominator is the cosine of pi over 12. And so the exact value of this expression is 1. D. We want to find the exact value of the tangent of pi over 6 minus the cotangent of pi over 3. So once again, let's look at the two angles. Pi over 6 plus pi over 3. Well, we get a common denominator, so we write this as pi over 6, copying it over. We write this as 2 pi over 6. We add these, we get 3 pi over 6. We reduce, and we get pi over 2. So what have we found out? We found out here that pi over 6 and pi over 3 are complementary angles because their sum is pi over 2. So let's rewrite the tangent of pi over 6 using this second identity. It would be the cotangent of pi over 2 minus pi over 6. And then I copy this part over. Now, this, according to what we saw here, can be rewritten as the cotangent of pi over 3. And so what do we have here? 0. Okay, now let's move on to another example. Example 5. Given the cosecant of theta is 6, find the exact value of these 4 expressions. Okay, now what you want to do here is use the most efficient method. So we have the definitions, we have the reciprocal, Pythagorean, and quotient identities, and then we have the cofunction of complementary angles relationships. So we go for what's most efficient. Well, let's see. The cosecant and the sine are related. They are reciprocals. This 6 is a whole number. It has a denominator of 1. The reciprocal of that would be 1/6. So the sine of theta is 1/6. All right, cotangent squared of theta. What do we know about cotangent squared that has a direct relationship to cosecant? Okay, well, we know this identity. We know that the cotangent squared of theta plus 1 is the cosecant squared of theta. We want to solve for cotangent squared, and that would be cosecant squared of theta minus 1. All right, well, we've just about got it because cosecant squared would be 6 squared minus 1, and so that would be 35. All right, what about this one? right away you should see that this angle in these parentheses, this angle is the complement of the angle theta. So I can rewrite this expression. The cofunction of secant would be cosecant, and then the complement of this angle is 90 degrees minus theta. The complement of this angle is theta. And so what's the cosecant of theta? Given as 6. All right, part D, secant squared of theta. Okay, well, it's certainly not going to have anything to do with cofunctions of complementary angles. And in terms of identities, there is no identity that directly relates secant or secant squared with cosecant. So I think at this point, the most efficient thing to do is to draw a triangle, label the sides, and then just read directly off of the triangle. So let's draw a triangle. It doesn't have to all be perfect here, but just enough to get the idea. This is the cosecant, so this is going to be the hypotenuse over the opposite, or you can read from the sign, opposite over hypotenuse. So this is 6, and this is 1. The missing side is 36, minus 1 is 35, and then we take the square root. Okay, so there are the 3 sides. Now, the secant is, think about what that is. It's going to be the hypotenuse over the adjacent. The way I actually remember this is I think of the fact that it's the reciprocal of the cosine. Cosine is adjacent over hypotenuse, and then I take the reciprocal. Okay, so what do I have here? And we must not forget that it is squared. So let's set up for that before we read. And we want hypotenuse, which is 6, over adjacent, which is square root of 35. And we square that, so we get 36 over 35. So in summary, how do you find the exact values? You use everything you know about this. You use the right triangle definitions of the trig functions when appropriate. You use the complementary angle theorem when appropriate. And you also use identities when that's the most efficient method. You need to study all of these relationships and master them until you are perfectly comfortable using them. Computing trig functions of acute angles. Let's first talk about 3 acute angles. We call these special angles. Let's look at a 30-degree angle, which is pi over 6, a 45-degree angle, pi over 4, and then a 60-degree angle, pi over 3, and let's talk about finding the trig functions of these angles. Let's take 45 degrees first. Let's draw a triangle, and we will choose this triangle to be a right triangle, but we want it to be written so that it is an isosceles triangle where these 2 sides have the same length. Now, it really doesn't matter what the length is of these 2 sides as long as they are the same. Let's try to make this look a little more like they're the same. So for convenience sake, I will just say that the length of each side is 1. So what is the hypotenuse? All right, let's see if we know how to do this. We're looking for C. So it's this side squared plus this side squared. Add them together and then take the square root. So it's going to be 1 squared plus 1 squared is 1 plus 1, which is 2. So this side is the square root of 2. Well, let's see. If this is an isosceles triangle, then that means that this angle right here is 45 degrees. And of course, that was by design because I want to study the trig functions of a 45-degree angle. So let's see what we have. Okay, well, we know that the sine, and of course this is pi over 4, and you want to think in radians as well as degrees. So we say that the sine of 45 degrees is the opposite over hypotenuse. And again, there is no need to rationalize unless you are specifically told to do so. The cosine of 45 degrees is adjacent over hypotenuse. And the tangent of 45 degrees is 1 over 1, which is 1. All right, these are the first 3 trig functions. You can get the next 3 by taking the reciprocal of each one of these. So we will just leave that to be done when we need it. Now let's look at a 30-degree angle and a 60-degree angle at the same time. Okay, so we have a 30-degree angle, pi over 6, and we're going to also look at a 60-degree angle. And how are we going to do that? Well, we're going to draw an equilateral triangle, or some approximation of an equilateral triangle. Now we have to be creative here. We know that if it's an equilateral triangle, all 3 angles are 60 degrees. I want to represent 60 and 30 and read from there. So what I'm going to do is, okay, I know this is 60 degrees. I'm going to drop a perpendicular which bisects this side. That means that this angle is 30 degrees. And what I'll do is I'll just say that the length of this side is 2, making the length of this half of the same length 1. It's very convenient. You, of course, could use any numbers, but whatever you do, the ratio is that this will be twice that side. Okay, what is the length of this side? Okay, it's going to be 2 squared, which is 4, minus 1 squared, so that's 4 minus 1 is 3. So the length of this side will be the square root of 3. Reading from the triangle. All right, let's do 30 first, which means I'm going to read this triangle. This angle. So this side is opposite, this side is adjacent. Okay, so I'm going to do the sine of 30, and then I'm going to read the cosine of 30, and then the tangent of 30. Okay, all right. The sine of 30 is opposite over hypotenuse. The cosine of 30 is adjacent over hypotenuse. And the tangent of 30 is, and you can either read it from the triangle, or we've done enough of this now that we know that it's going to be 1 over the square root of 3, because we can use the identity, the reciprocal identity, that the tangent is the sine over the cosine. Okay, we can get the other 3 using the reciprocal properties. All right, now let's read the trig functions of the 60-degree angle. So we want the sine of 60, or pi over 3. We want the cosine of 60 and the tangent of 60. Okay, the sine is going to be opposite over hypotenuse. And then at this point, you might start to realize that cofunctions of complementary angles are equal. It means that the cosine of 30 equals the sine of 60, and the sine of 30 degrees is the cosine of 60 degrees. We don't necessarily have to read all of this. And then the tangent of 30 is going to be the opposite over the adjacent, which is the square root of 3, or the reciprocal of, well, let's not, we're not going to have cotangent here, so we're not going to write all those down. You can figure those out using the reciprocal. Okay, so what do we have here? We have some things that would be very convenient to memorize. So what we want to do is we want to make this little table. Okay, and you want the table, and I'm going to just write it in right here. You want the sine, the cosine, and the tangent. and this needs to go in here, of 30 degrees, 45 degrees, and 60 degrees. And this is something you want to write down over and over and over and over again until you are just totally comfortable with it. Okay, so what do we have? We have the sine of 30. Okay, now that's this batch right here. Okay, so we have the sine of 30 is 1/2. The cosine of 30 is the square root of 3 over 2. And the tangent of 30 is 1 over the square root of 3. Okay, next column would be these. Sine and cosine are the same. You see how easy this is to memorize? You just get comfortable with it. And then the tangent of 45 is 1. And then we have this last batch. And so we have the sine of 60, which of course is the cosine of 30. So these are easy, they're just switched, and then this one is the reciprocal. This right here is so important. You will use it over and over and over again. Let's take a look at some examples where we use this information. Example 1. Find the exact value of each expression. Notice that what we have here are all trig functions of acute angles, but not only that, all of these acute angles are special angles. Below I have the table that we generated by drawing the triangles for 45, 30, and 60 degrees and finding the trig functions from there. You can of course use the triangles or you can use this table. All right, so let's see what we have. The sine of 45 degrees. Okay, the sine of 45 degrees is 1 over the square root of 2. We want to multiply that by the cosine of 30 degrees. The cosine of 30 degrees is the square root of 3 over 2. Now, what we're really doing here is practicing using this information. So we're going to multiply here, and we will get the square root of 3 over 2 square root of 2. Let me point out right here to you something about rationalizing. The sine and the cosine, in particular, say of 45 degrees, are 1 over the square root of 2. You don't have to rationalize, but if you chose to do so, you would multiply this expression by the square root of 2 over the square root of 2, which would then simplify, and you'd get the square root of 2 over 2. What you want to do is recognize that if you ever see this expression, it is equivalent to the 1 over the square root of 2 and also to this one. The same thing for this. This is actually equivalent to the square root of 3 over 3, and so you may see that at some point too. All right, let's go to B. The tangent of pi over 4. Okay, well the tangent of pi over 4 is 1, and the sine of pi over 3, which is 60 degrees, is the square root of 3 over 2. Now how can we simplify this? Well, we can get a common denominator, so we write 1 as 2 over 2, and then subtract the square root of 3 over 2. We can combine the terms in the numerator over the denominator. Okay, let's look at the third one. The tangent squared of pi over 6. Well, the tangent of pi over 6 is 1 over the square root of 3. And what we want to do is, from here, we want to square this. Then we want to add sine squared of pi over 4. So the sine of pi over 4 is 1 over the square root of 2. Don't forget to square it. And what do we get? This would be 1 over 3 plus 1 over 2. Common denominator, this would be 2/6, 3/6, exact value 5/6. All right, so what you need to do is memorize the trig functions of the three special angles and be able to use them quickly and efficiently. But what happens if your acute angle is not one of those three special angles? Then you need to use a calculator. Let's take an example of that and work out some exercises using the calculator. Example 2. Find the value correct to 2 decimal places. Notice that these are all trig functions of acute angles, but none of these are special angles. And so we're not going to be able to read off of the triangle or the table that we've memorized. Instead, we're going to have to look up these values that are stored in our calculator. Okay, the big thing here is units. Degrees, radians, degrees, radians. Your calculator must be in the correct mode in order for you to get the correct answer. All right, so this is the sine of 48 degrees. Make sure your calculator is in degrees. The default is usually degrees, but you should always check that. Okay, so I'm in degrees, and now I want the sine of 48 degrees. Now, depending on what kind of calculator you have, you may have to enter this. If you have sort of an old-fashioned scientific calculator, you may have to put the angle in first and then the trig function. If you get one that has a display, which is what I would recommend, it's much easier to work with. You can depress the sine button, and then you can put in 48. It's already in degrees. Enter. And out comes the answer, and then I want to round correct to 2 decimal places. I get 0.743, and so when I round, I get approximately 0.74. All right, what unit is this? Radians. So clear your calculator and put it in radian mode. Okay, I'm bringing up radian mode. I am selecting it, and it now says radian mode. I want the cosine of pi over 12. So that's pi, and there's usually a key for pi, and then divided by 12. Enter, and I get 0.9659 and so forth. Rounded to 2 decimal places is going to be 0.96. Okay, now let's see. This was 9659, so you know when I round this, it should actually be 0.97. Be careful when you are rounding. Okay, let's clear the calculator, and let's go back to degree mode. Okay, so mode, degrees, enter. Okay, I'm in degrees, but this is the secant of 17 degrees, and if you look at the calculator, it has sine, cosine, and tangent. So how can I get the secant? Well, that's what we learned all those identities for. This is 1 over the cosine of 17 degrees. So let's enter that information. So it's 1 divided by the cosine of 17, I'm in degrees, enter, and I get 1.045, blah, blah, so this is going to have to be approximate because I'm rounding, and I'm going to get 1.0, and I have 45, so I'm going to round to 1.05. Okay, what about this one? Mode, correct. So clear the calculator, go back to radian mode, enter. The cosecant is 1 over, and I have to rewrite this in terms of either sine, cosine, or tangent. And what is it? Sine of pi over 5. So I'm in radians, and I'm ready. It's 1 divided by the sine of pi divided by 5, and that is equal to 1.701. So that is going to be approximately 1.70, correct to 2 decimal places. And so this is the process you use to find the trig functions of acute angles when they are not special angles. You use your calculator. If you have a special angle, either 30, 60, or 45 degrees, you should know that information by heart. Practice it until you do.